Okay, okay, guys. So this week we are actually transitioning. Last time we were like until like last 2 weeks, we were focusing on cache side channel attacks. So in the memory hierarchy, we are now going to focus on memory at least for 2 weeks, this week and the next one. So the way attackers can launch their attack is not that they can only exploit the side channels in the different hardware components, but they can also exploit different programming bugs in the software, which is written by users. And by exploiting those bugs, you can do many different things as an attacker. Okay. So definitely we cannot cover the whole topic in its complete depth. I'm not talking about the paper, but the overall topic of memory corruption attacks. We cannot cover it, but the purpose is to give you an idea or to give you an introduction of how things work and what is the basic terminology and what are the basic or the fundamental approaches to defend against memory corruption attacks. Okay. So this paper, which we are going to address, which we are going to discuss in this week, it is again not a research paper. Systemization of knowledge basically means that whatever was already there published in context of both the memory corruption attacks and the defense mechanism against memory corruption attacks. So in this paper, they have tried to present it in a systematic way and to give a unified framework to understand and to reason about the existing attacks, which exploit the memory bugs in the application codes. Okay. Okay. So the issue is that the lower level languages, like for example C or C++, the good thing about them is that they give you the direct access, or actually they allow the manual manipulation of the memory by the program writer or the person who is developing the application. So it gives you like more control, but at the same time, as a result of giving this more control to the programmer, the programs written in C or C++, they are prone to memory corruption bugs, because we cannot take, like, it is difficult for a normal person to write a program and then guarantee that there are no programming bugs in that program, right? There are automated tools, there are tools available which you can use to, like, for example, identify and detect the potential programming bug, and then they can make you suggestion, okay, do this correction to avoid this potential vulnerability. But there is no like 100% guarantee that you will be able to write a bug-free code. And these bugs, they are exploited for changing the behavior of a victim application or to hijack it completely. I will try to show you an example attack, how such a programming bug can be exploited to hijack a victim application. Then one can ask that, okay, if that is the problem with C or C++, then why we cannot stop simply using those programming languages for developing any more future programs or future applications? The issue is that C or C++, it has been used for like so many decades, both of them. And there is billions of lines of code, existing code, which you cannot like replace. One thing, and second thing is like, I think this is true for all low-level languages, or even like, for example, if you go down to the assembly, yes, it is difficult to write the code because the abstraction, the syntax used by assembly language, for example, is more farther away from the human understanding and is more like closer to machine understanding of the things. And when you go to binary, it is like now humans cannot read it at all, but machine can understand. But yes, the ease of programming reduces, but the control you get, the performance you can extract, it improves as you use the lower level languages. Okay. So these are the two reasons because of which we cannot argue that, okay, simply uh, get rid of C or C++. And C or C++ is also used heavily in developing the system software. For example, the whole code of Linux is written in C and in assembly language. Okay. So, so at the time of writing of this paper, there were like a wide range of attacks which were exploiting these memory bugs, and also a lot of defense mechanism to protect against them. Then the question is like, if that is the situation, then why you need this paper? Already their attacks are published, there are defense mechanisms to, to protect against them. But the issue is that most of those defense mechanisms, they are not deployed in uh, the commercial systems. Why? Because of multiple reasons. Because they have huge performance overhead, or they are not compatible with the legacy software, and maybe the protection they offer is not complete. Maybe they protect like a subset of program bugs, but not all of them. Maybe they protect against how a particular program bug is exploited, the mechanism of exploitation. But if a different mechanism is used to exploit the same bug, the protection will fail. And they also change they require the changes in the tool chain. So why they are writing this paper? Because the issue is that for community of researchers who are working in the area, or for even like technicians, it is difficult to see that, okay, we have so many defense mechanisms. So how we can figure out which defense mechanism is efficient and effective against a given type of attack. And there is no mechanism, there was no like framework to compare multiple defense mechanisms against each other, based on their effectiveness and efficiency. And also, they want to address that what are the challenges in implementing those solutions on real systems. So the motivation behind the paper is to synthesize and evaluate the previously proposed defense mechanism. And actually, I think they have done a good job when they are like they are presenting the attack model in figure 1. So they have covered almost all type of, at least at that time, almost all type of memory corruption attacks, and also the defense mechanism which you can use to protect against them. So it gives you a holistic view of the whole domain. So they, in their contribution, they have a general model for memory corruption attacks, and then they identify different enforceable protection mechanisms based on that model. In the next figure, we are going to talk about that model. Any questions here? How many of you are at the paper? At least pass one. Okay. Yeah. Pass one means like introduction, background, conclusion. Okay. Okay, so then if you have done the past one, then you must have came across so many terms which are not familiar to you or which are new to you. So now I want everyone to tell me one terminology, one concept which you don't know about and you want to know in this lecture. Tell me something which you have read in the past when you're doing the past one, and you came across something which you don't know what it is. Temporal errors. Okay.
Address space layout.
Wait, let me take the note. Temporal error. Okay. Yes, Allah.
Yes.
Next. Next.
The depth, WX or X.
What?
The depth WX or X.
I haven't gone through past one yet.
Okay, you, next.
What is that return-oriented programming?
Next.
All the different forms of attacks. Like,
Sorry?
all the different forms of attacks, like stack cookies. Stack cookies is one of them. I don't know.
Okay. I am not sure if stack cookie is same thing as canaries or not, but let's say I'm writing it as stack cookies. Okay, next.
Special order.
Special order. Have you read the paper, Al-Nazir? Okay. So let me go through the slides, and then at the end, I will come back to these questions, or these, to try to explain what these are. Okay, so this is their the attack model they have presented. Actually, as I said, it covers almost all different types of the memory corruption attacks and the defense mechanism against them. So before we talk, before I go through the slides, so let's have a look at the picture itself. So each rectangle here, for example, it simply shows you one step of the attack. So, and the outer one is like, okay, what policy or what defense mechanism we can use to protect against this step of the attack. So each attack is like consisted of 6 steps, but each step itself can be completed in multiple ways. For example, step 4, you can complete it by doing one of these things. Any one of these things. But then, and this green rectangle is showing you, okay, what policy or what defense mechanism you can use to protect against this step of the attack. However, if you want an attack to be successful, it needs to be successful at each step, which basically means it needs to break the defense mechanism of each step. Okay. So an attack, it consists of multiple steps, and each step can be performed in more than one ways. So for a successful attack, the attacker must break protection enforced at each step by the defender. So it is not sufficient, like, for example, let's say, if you break the defense mechanism, data integrity, but you are not able to break the memory safety mechanisms or data flow integrity mechanism, then your attack will not succeed. So we are going to first have a look at an example attack, like an attack which follows all these steps and then becomes successful. Definitely for this example attack to become successful, we are making so many assumptions. And I ask you to be attentive and have a look at critically from the example, so that you can ask, okay, what we are assuming here? What is unknown here? Okay. So we will first do an example attack, and after that, if time permits, then I will try to go through the other part of this figure. Okay, so you cannot read it back. Okay. Then do something. Yes. And you don't, right? Okay. So let's first have a look at this example code, and then we will see how, if this is the example code, how an attack can perform different steps in the context of this example. So let's say we have 3 functions: add, subtract, and multiply, and all of them are doing very simple things. You give them 2 numbers, they do the operation, give you back the result, right? And then let's say in the main function, we have like print hello world anyway. So then we are defining a function table. So this is like function table actually is what we are going to do is like it is an array of function pointers. So how you define it, like you first define just like for example, if you define a regular array, you have to array of like say integer numbers, you have to first give the data type, right? So similarly, when you are going to make an array of the function pointers, you have to specify both its return type and its type of parameters for all the functions. So here we are saying all the functions, they take two integer inputs and they return the integer value, right? And we are initializing the array. We can initialize the array of function pointers by the name of function themselves. Remember that functions in C and C++, their name themselves are pointers. So when you refer their name, it's basically means you are referring the address of the code where body of that function is residing in memory. Okay. So here we are storing the address, okay, of these three functions. And let's say after that we are making a function pointer of the same type as of our array. Like this function pointer, it also returns an integer, and so job of the function pointer is to point to a function. But then we need to define that what type of functions it can point to. It can point to the functions of the type which take two integer input values and which return an integer. Okay. And now let's say in our code we are saying, okay, function pointer is a function table, and from which index or element we read from the function table, that index is provided by the user. Okay. Definitely, I mean, this is a programming bug, right? So if there is, as I said in the start, if there is no programming bug, you cannot exploit, you cannot launch the memory corruption attack. For memory corruption attack to be feasible, the first step is there should be some programming vulnerability, programming bug in your code. If not, then you are safe. Okay. So intentionally we are like, this is our try example. So that's why we are saying, okay, it depends on the user input. And after that, we are calling that function. For example, let's say if our user says that input 0, then it's mean that function pointer will be actually pointing to add. So what will happen, that for and add function will be executed, and 4 and 10 will be added. And if you print the result like printf, whatever is printed by whatever is returned by this one, you will see 14. Okay. But if like you put like, let's say user input is 1, then it will do 4 minus 10, and if 2, then it will be 4 times 10. Clear? Okay, so I have explained this one. Okay, now how this looks like in memory, what is the memory layout of our program, focusing only on data, not on the code. So this array function table, it has 3 indexes. Let's say I'm just trying here. Let's say these are the 0, 1, and 2. So 0 points to add, 1 to subtract, and 2 points to 3. This is how it will look like in memory, right? Now, assume that we are making assumptions, right? So assume that attacker is able to write in memory, some malicious code, and then it has a variable. It knows like it has a memory location which is at index 10 if you start from here. So which is like 11th element at the distance of starting from 0. So 11th element, what it puts is the address of this malicious code. And so basically here it points to the malicious code injected by the user, by the attacker. Okay. But again, now here are so many questions. The question is like, okay, how can attacker inject the malicious code in memory, right? And how does the attacker knows that from where this array is starting, what is the starting address of the array, right? So there are so many unknowns, but for the time being, we are assuming that attacker has the capability to do that. Okay. So this malicious code, it can be an injected code, or it can be an existing gadget. Basically, existing gadget basically means that it is possible that this malicious code actually is a code, let's say it is another function within the address space of the victim. Let's say it is like scale, which is not given here. Okay, so you have add, subtract, multiply, and scale. So, but here the intention of the programmer or the victim is never to invoke the scale, right? Because you are saying only add, subtract, or multiply. But what I can do is, for example, I can say as an attacker that I can redirect your execution in such a way that when you want to execute add, actually it will be doing scale. And as a result, whatever computation you are doing, you will get the wrong results. And any decision you are making based on that computation, they will be flawed. Okay. And again, here is an assumption that even if it is not injected code, it is a code of an existing function, for example, scale, then how I know what is the address of that scale function in the address space of the victim. But again, I'm assuming that there are ways which you can use to figure it out. But for the time being, we are just assuming that I have the capability as an attacker to know that address. Okay. So let's say when you ask the user to give the input and user says 10, so you are done with the first step, which is basically make a pointer to point out of bounds. So your legal bound was only 0, 1, and 2, right? So when attacker says the input is 10, so you are pointing to some memory location, which is not within the legal bound of your array. So for that, in order to prevent that, what you can do is that you should do the bound checking that whatever input is provided by the user is within the valid range. But again, we are saying that this program is but it is not free of bug. Okay, and then once you have this, like let's say user input is 10, so you are able to index a location which is out of bound of the array. The second step is to use pointer to read. How we can use that pointer to read now? Definitely, if you have index 10, you will read function table. So remember in the previous figure, you will go into a different location, right? And you will read from that invalid pointer. So that second step is also completed. And once you have read from there, the next two steps are that you need to modify a code pointer such that it points to the address of a shellcode or gadget. So remember, we had this figure, right? So when you load here the function table from index 10, so what you are doing is it will be read on the right side of the statement. On the left side, it is a function pointer is being read. So you are writing another pointer in the code. So after writing that function pointer, when you will, as a result of writing that function pointer, what happens that your function pointer will be now pointing to your malicious code. It will not be pointing to your legal, valid functions, add, subtract, or multiply, but it will be pointing to this one.
When you use a pointer to read it, could you use that to find the address of where it is?
When I use the pointer to read what?
Can you use that to find the address of where the function is?
This malicious one?
Or just where those functions are, like that, subtract and multiply?
Yeah, so as I said, as an attacker, I'm assuming that I have that capability. It's not shown here how. But if you don't know address of for example, as I gave scale example, if you don't know the address of the scale function as an attacker, you cannot launch the attack. If you're not able to inject that code, you cannot launch the attack. If you're able to inject the code, but you don't know at what location you have injected the code, you don't know the address of the injection point, then you cannot launch the attack. Okay. So here, what happens, let's say the older value of the function pointer was like 0x(a) 0 something. And what happened now, it will be overwritten with this value, 0x(ba). Now function pointer as a result will be pointing to this malicious code. And
Every time the C program runs, wouldn't the memory address change? So wouldn't that make it more difficult to?
that's correct. That's correct. So we are making so many assumptions here. There is no ASLR, there is no data space randomization, there is no memory safety, there is no data integrity, and so on. Okay.
Okay.
So we just want, at this time point, we just want our attack to succeed. Okay. Yeah, that we are assuming there is no protection. Okay. So. Okay. So in the next step is like you want you want to use the pointer by calling an indirect call, by making an indirect call. Basically, it means like when you use the function pointers to invoke the function. So what is the advantage of using function pointer instead of like I could have said here directly call add or subtract or multiply. Why I'm using function pointers? Because by using the same function pointer, I can dynamically decide which functions should be called. At one time point, maybe it is add, next time maybe it is subtract, next time maybe it is multiply, but using the same function pointer, right? I'm making decision maybe based on some conditions or based on some input, right? So when you use a function pointer to invoke a function, so you are making an indirect function call. And what happens as a part of indirect function call, that your instruction pointer or program counter both are the names of the same thing. So your program counter and instruction register, they are loaded with the address of the entry point of your target function, which is pointed by your function pointer. So basically, what we are saying is that since now a function pointer points, holds the address of 0xba, which is actually the address of this malicious code. So now your instruction pointer will be loaded with the first instruction in the body of that malicious code. And the next instruction that will be executed, it will be that malicious instruction. So, which basically means that your control flow has changed. So, which basically means that it will start executing your injected code and your attack is successful. So what have you done here? Basically, you have changed the control flow, or you have hijacked that control flow. So if you are using your injected code, maybe you can use the injected code to hijack the victim process or victim application. And if you are like, let's say, not able to inject the code, but able to use an already existing code, so you are able to modify the control flow of the victim. So question that, okay, just like quick, very high level understanding of how you can inject the code. Actually, you can do it on your Linux if you want. On Linux, you can, there is an option. I don't remember, but I did it like 2 years ago. So what you can do, check on Google, there is an option where you can say, okay, disable write exclusive X protection. So which basically means that now if you write the data, so this is your stack, okay? So anything which is written in the stack is data, right? So if it is data, this protection says that you cannot execute it. You cannot execute it, right? But in Linux, you can disable it, this protection temporarily, let's say. Even you can disable ASLR. So let's say you disable it. Then if you are able to put some code on this stack, and then somehow you are able to point your instruction register or program counter to first instruction of your injected code, it will execute that code. Now, how you can inject the code on the stack. Okay, now let's say you have this C program, or some function foo, and it takes some input from user into a character buffer, let's say of size 20, and user gives some input. I'm not writing the complete program, but I'm just trying to explain. So then when you say, okay, give some input or provide some input, user enters the value of, let's say, a value with a string with 100 characters. So now what will happen, like this buffer is, it depends that where is this buffer, how you have allocated it. If it is a like array, then it will be, I guess, in stack. But if you have like, let's say malloc, and then it will be in heap, okay? So now those, let's say we are assuming it in stack, okay? So what will happen is like those 100 characters will be written, but in memory you have reserved only 20 bytes for that. So when 100 characters will be written, so what will happen? What will happen? Let's say this was your buffer, and starting from 0 to, let's say, 90. So it will start writing all these locations up to 99. Okay. But when you, as an attacker, when you give the 100 characters, it doesn't matter for the program whether you give some random characters A, B, C, D, E, F, or the binary codes of a program, binary code of a program, right? So if you have binary code of a program and you translate it into the ASCII code, and then you can just write that ASCII code of that program here, what will happen? All those ASCII characters will be written here, right? So now, if let's say after writing that, this is not like, this is, we are doing our buffer overflow. So after overflowing the buffer, if let's say you are able to point, if somehow you are able to point the program counter to this location. So this is your first instruction in the program, which basically mean that, actually I did it, so which basically mean that you will write the ASCII code of your program in reverse order, so that the first instruction is at the top. Okay. So if you point program counter somehow here, what will happen? It will execute this instruction, then next, then next, then next. So program counter, so stack is, we are saying, it depends how your stack behaves. Is it going upward or downward? But anyway, you can adjust it accordingly if you know how your stack is, in what direction it is going. Okay. So as a result, what will happen? That you will be able to successfully inject the code. But there are then so many things. We are, for this to be achievable. One, there is no buffer overflow protection mechanism, we are assuming. Second, this protection is not enabled, okay? And even like if it is a multi-stage attack, so then we also need ASLR to be disabled. For example, in my case, when I did it, I had to disable this one too. Okay, otherwise it will not work. Yes.
So this attack that you're defining here is the spatial errors. Falls under that.
Okay, who want to answer that?
You're doing the buffer overflow.
Say louder.
The buffer overflow, is that what we're doing here instead of the ASLR for the whatever which whatever seems said?
The attack, the buffer overflow, his question is the buffer overflow, does it fall under the category of spatial error or not? Right? This is the question.
Yeah.
Anyone? What is spatial error? Who knows?
From my understanding, well, I'm asking more clarification. It's the idea of just having memory out of bounds that you're then altering and then telling the program, go over here and like this. And then
So spatial error is when you do something wrong in the memory space, like you are writing or reading from the place where you are not supposed to read or write. Okay, and here this is what we are doing. We are not allowed to write beyond 20 characters. We should not be. We are allowed, but I mean, we are supposed to be not writing beyond 20 characters. Okay, so that's why it is like special error. Okay. Any questions? Then the figure in the example.
Like the example you give here, does it also fall into like?
Yeah, this is a buffer overflow, so yes. And in the example, we also what we're doing the indexing, like index was given by the user, but again, it points to a location where we were not supposed to read from. So it is again a special error. Okay, so okay, let me first answer your questions, and then I have a set of background questions of items which I can discuss. Okay. So, okay. Who want to answer what is temporal error?
Okay, try that one. So that one is more the focus of, actually, I have it up here. It's, whenever memory is free, and it has like a pointer location. We're going in there, so it's like a pointer to a function, and then we deleted that function in our code. What we're gonna do is we're going to, as soon as that's deleted, we're gonna replace that pointer and we're gonna reinsert it and say, no, actually the pointer does exist and point it to our function as an attacker.
Oh,
Or is that too complicated?
yeah, I understand what you are trying to say, but it can be said in a more.
So we're just changing the pointer to be something of our own pointer as an attacker that the attacker defines. Whenever a memory location is free.
See, it is error. We as an attacker, we are not doing that. Programmer has a problem when he or she was writing the code. Okay, so you want to say something?
Yeah, that's fine.
Okay, so here is a concrete example. So let's say you have a pointer P and you say malloc of let's say 64 bytes, a size of any object. I don't, you made us an object of some class and then you say size of that object. Right? And then you use that pointer for something, for some processing. You are doing something on that object. And when you are done with your processing, you said, okay, free P. So here, when you said malloc, that basically what happened that in memory, depending upon what is the size of the requested size, let's say it is 4 kilobyte. So you were allocated a chunk of 4 kilobyte, right? And remember, in previous paper, we learned that we can track the way to track whether a memory chunk is allocated or not, that one way is to maintain a bit mask. So let's say we are maintaining a bit mask, which tells us whether a block is allocated or not. And let's say that value for this particular 4 kilobyte chunk is 1, which means it is allocated. So this is what is the like state of things at this point. So when you are done and when you say free P, what happens is like this is set to 0, okay? And now the memory allocation manager, now it knows that, okay, this chunk is free and I can use it for future allocation requests, right? And one more thing which happened was like, let's say here, this was the starting address on 0xF0 something of this 4 kilobyte. So this was placed here, right? So when you say free, the bit is set equal to 0 and then manager marks it for future allocation. It is a like potential candidate which I can use. But this P is not set to null. P is still 0 pointing to 0xAF0. Now it is a pointer pointing to a memory location which is freed. And this is called dangling pointer. Now, if you use this dangling pointer, after it is being freed, if let's say you say printf p, so you can put the format string on your own, but I'm just saying print p0, which basically means print the first byte of from this address. So it will still print it. Okay, so I'm using the pointer once it has been freed. So this is known as temporal error. At some time, it was correct for me. It was right for me to use this pointer to access the memory location. But after a certain time point, I am not supposed to use it. Right? So this is like dangling pointer, and which leads to temporal error. Okay. Clear? Okay, maybe I can start with the easier one. Stack cookies, maybe I'm not sure, but I have this feeling that stack cookies mean the same thing as canaries. Maybe you can do a Google to check. Sorry, same. Okay. So I'm just going to explain how stack cookies and canaries work. Okay. So remember in buffer overflow what you do. So how even like let us step back a little bit more and how see how stack is used. Okay. So let's say you have a function foo, and let's say you are in the main function, and then you call foo, and in the body of the foo you have another function, what they normally use, foo and bar. Okay, right? So when you are, and here you have another statement after this, and here also you have another statement. Okay. So when you call foo, when you are in the main, what you need to do is that you first thing you do is that you store the return address where you are supposed to come back once you are done with the execution of the foo, right? So let's say I'm naming it as return address 1. Okay. So I will put it on the stack. Okay. And then foo will be executed. When foo will be executed, first its input parameters, they will be copied on the stack. Let's say input parameters. Then in the body of the foo, let's say you have some other local variables here, X, Y, Z. They will also be created here on stack. Okay. And then let's say after you did this one, X, Y, Z, you call the bar. But before calling the bar, you have to push on the stack return address 2. Okay. Now let's say I am pushing return address 2 here, right? And then the body of the bar will be executed and so on. Like same thing will happen. This parameter will also be copied, and whatever, if it uses some local variables, they will also be pushed on the stack. Okay. Now let's say you are done. Like let's say the body of the bar is empty. Okay. So you just call it and come back. That's it. So now what will happen when you come back? So in the program counter, so when you enter the body of the foo, what happens that program counter is initialized with the starting address of the foo. Let's say the starting address of the foo here is address X. So program counter was initialized with address X, and then after that it starts incrementing. Okay. And once you are done, so at the return, what happens? So it will pop up. So after, like, let's say after the bar, what will happen? Maybe I can simply remove it. So once I am done with the foo, so these will be like popped from the stack. Okay. And then my top of the stack will be pointing here. And what I will do is like, I will put the value of this return address 1 in the program counter, and this is how I know where to return back in the main program. Okay, so this is how, like, how stack is working. Okay, now how stack is exploited is, like, let's say you are an attacker and you start, there is a buffer. So let's say stack is located in memory. Everything is located in memory. And let's say you have a buffer here somewhere. So, and you overflow this buffer. Like, let's say you know that you have a malicious code, just like consider the previous example, and you know the starting address of that malicious code. And let's say that malicious address is MADR, malicious address. Okay. What you do is that you overflow the buffer with repeated values of that malicious address. So what will happen? You will have malicious address here, malicious address here. It will overwrite everything. Okay. And now when you say return, in PC, it will put the malicious address. Okay. And as a result, now the control will go back not to your main function, but to your malicious code. Now, how the canaries or stack cookies are used to avoid this, actually to detect this, not avoid this, only to detect this, is that you put the, in the stack, you put the cookies, I think before or after your return address, like some known values, which are known as cookies or canaries. Okay, some known values, you put them there when you are entering the function. And when you return, when you call the return, you check whether the values you placed in the stack are the same which I find now when I'm returning back. If they are same, then it's mean that the stack was not overwritten. But if they have changed, it's mean some attacker has overwritten your stack. Okay, because remember, if I have put a canary value here and a canary value here, and now if you overflow it, you will overwrite my canary values, right? So then I can detect, okay, yeah, someone is like playing with my stack. Okay. Okay, second question. Any questions or comment?
Yeah, how? So can an attacker like see that there have been stack cookies or stack canaries put in, and is there a way that they can go around triggering them at all? Or?
Yes, definitely. Canaries have already been broken long time ago. I don't remember now what are the exact details, but I read a paper where they explained how to avoid the canaries. So, for example, what you can do is, like, if you have a mechanism where before overflowing, you can read the canaries values. As an attacker, I can read the canaries values. I can overflow the buffer and then put back the canaries value, but I still malicious address is there. Now, when you will try to use the canaries for detection, you will think there is no attack, but there is attack. I mean, this is what I vaguely remember from the paper, but there is mechanism to detect.
And then do they put them every single time a function is called?
Sorry?
Are they placed in every single time a function is called?
Every time?
Or like when do they put them in? Is it like every function return address when you make a return address? Is it, so if you have like a return address 2, would there be a cookie or?
Yeah, every time. So whenever you are making a function call and you are pushing the return address on the stack, you have to put the canaries on the stack. So definitely increases both you're doing extra time, extra work, and it increases both your time and the memory space.
I remember from the reverse engineering class that we exploited a program using format string vulnerability, where we defeated ASLR and stack canaries, inputting format strings such as %p a couple of times to leak information about the addresses, and then write an overflow to the buffer.
Oh, okay. So ASLR was enabled when you were doing that?
Yeah.
So was it like? But in ASLR, you actually randomize the address, right? But address at not at, you don't randomize at fine granularity. You randomize at coarse granularity, like for example, at granularity of libraries or some other granularity level, not for every address, right?
Yeah.
So how you then were able to find the address of like,
Because the problem we had to exploit had this vulnerability where it was using a function called string copying, I guess. And the string copy, I think passes the string as a string instead of formatting it into something else. So if you input percentage %P or percentage %C, blah 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 blah, it's going to leak the addresses. And then if you put something before the between the addresses, you can calculate the offset and then write an overflow of certain amount of bytes to write the return address, to overwrite the return address.
yeah. Actually, for those who don't understand what he's talking about, so the thing is like when you say scanf, so you can get a string from the user. Now the string you get from the user, if it is a formatted string, so then you can exploit it to print the content of given memory locations, if you know the address. So for example, if in your program, let's say you have a program and it says, okay, scanf, and here before it says, okay, printf, enter your name, okay, and then it says scanf. So then I, as an attacker here, provide a formatted string, let's say I say %x, and then I can specify, okay, how many bytes, like let's say, I guess let's say 4. So what I'm saying is that it will basically print the content of the 4 bytes from the stack, because scanf is not checking that whether I am giving a supposedly valid input or not. Okay, so if I can do that, so it can give me the content of stack locations, which is basically I am leaking the information. Okay, and using this, you can like get an idea of how ASLR is working. Not exact like, can you break exactly? I mean, or you can like a educated guess of how ASLR.
Kind of like an educated guess.
Yeah.
Yeah.
So, so okay. Any other question, comment? Okay, so we are done with this one. Okay, special error. We have already discussed, right? Yeah. Okay. Okay. Okay, let's talk about this one first. Write, exclusive, or execute. So this is protection, but let me give you first like the background, why what it does, but what kind of vulnerability it against what kind of vulnerability it gives the protection. Oh, okay. You don't need to even like. So remember here I put the address of the malicious address, but here I'm assuming that I am even able to inject the malicious code somewhere in my memory, which can I also do you by simply doing the buffer overflow. Okay. Let's say there were 2 inputs. User were asking for 2 different inputs. For first input, I did the buffer overflow to inject my own code. Remember, I told you like you can have the ASCII code of your binary and just provide it as an input string and it will be written there. Okay. And then the second buffer overflow, I use it to overflow the stack and put the value here. And now this points to the starting address of my injected code, right? Now, what I have done, I have injected the code. So this basically means I have written the memory location, right? And then for this attack to be successful, when PC will be pointed to this address, the instructions from that point, that memory location will start executing. So one thing I did is I write a memory with my own. I write a memory with my own code, and then I execute from that memory location, right? Execute from that memory location. Right? So, but you can you can protect against this kind of attack if you say that, no, you cannot do two things on the same page, on the same memory location. You cannot do. Either you can have a page, either you can write a page, but then anything written in it will not be executable. Or a page will be only readable, and then whatever is written there is executable. So like as a user in user space, you cannot write it. Okay. So if that is the case, now let's say if I'm able to write, but it is not executable, my attack will fail. Right? So this is what is done here by this approach, that you make it exclusive. A page is only in one of these two states. Either it can be written or it can be executable. Both things are not, both operations are not possible for the same page.
This check is done on the attacker process, right? Where it's saying the attacker can't write and execute, doing the same when it enters stack.
Remember, it is not the attacker who is executing. It is your processor who is executing, right?
Yeah.
Attacker is simply writing to a page. Let's say if you are successful to write a page, and then you are successful even to load the program counter with the starting address of that page you have written. Now your hardware says, okay, this page is marked as not executable. So it will throw an error. Okay.
So as it isn't executable, would there be any way that it would become executable in the future, like in a different page, or I'm trying to get clarification on this? Like, the processor wrote data, but it needs to be executable in the future. So how would it become in the executable?
I don't think so. And the basic, my reasoning behind that is this, that you put your code in your read-only pages. So read-only pages, then you don't allow them to be changed to be writable during the program execution. And normally there is separate program segment and code segment and data segment in the address space of each process. So readable pages, they are in a different segment, and pages which can be written, for example, to hold data, they are in different segment. So even if you have, let's say, a readable page on read-only page, so if it is even reused in the future, it will be used only for the read-only purpose, to hold the code, not that.
Okay.
Did I answer your question? Or I confused you more?
Yes and no. So it's just, there's no need for it to be executed in whatsoever purpose. It's just,
Yes.
okay.
If there is a need for it to be executed, it will be marked as read-only page from the start.
Okay,
So it will hold only code.
okay.
And then, so I imagine in like a Linux system, a super user can probably change it to be both read, so both write and executable, and that wouldn't like give issues, would it? It would still like let you do that, or would the system actually?
So as I said, you can change this setting. You can basically disable this protection.
But you can do it with like chmod for every single file individually, or do you have to like actually change the settings?
No, then it is, if I remember correctly, if it then disabled system-wide. It is not like you disable it for a particular application, or at least I did it system-wide.
But you
Let me say like this.
can go and chmod each file technically in Linux. Like, so these files you can like
Yes.
chmod plus X,
Yes.
it's like a write only.
Yes, yes.
And then it would still. would let you do it.
Yeah. But even like, if you do that, you are doing that for files, right?
Mhm.
But when you, let's say you have a file which holds the binary of a program, So that file will become executable or executable, right? But here we are not talking about that file. We are talking about the stack. When, let's say that file is a program which has a vulnerability, and then we exploit that vulnerability to override the stack. So when you say this file is executable, only the memory location which holds the code of that file, only those locations are executable. But we are not interested because it is by default executable. That is not our target. Our target is to execute an injected code.
Is the designation of whether it's writable or executable done when you're carving out stack in your program execution? Like when you're calling main and it carves out that portion of stack and you put copy main there? Is it designated then, or even before then, when you move the page from memory into, from not main memory, from storage into main memory? Is it designated then as this page is writable or executable, or at the function level where you're saying this, when I'm carving out the stack?
I don't know, and I don't want to give you wrong information. Sorry for that, but I am not sure, but I would not expect that it is done. It should be done by the operating system. Well, that is I'm sure about. Because it knows like where the code is located for a given application, and then it should mark those pages as read only. And the other pages are they are not read only and executable, and the other pages as writable but not executable. So I would
So
expect.
it's designating each segment of memory separately.
Yeah, that's true, but I mean, still, like, if you don't have this protection, so what are the core segments? So, like, you have data segment, core segment, heap, stack, right? So normally core segment, as clear from the name, contains the code, right? Now data, heap, and stack, all of them contain different type of data actually, right? Now, if I can do an buffer overflow in heap, let's say, and by doing the buffer overflow, I can inject the code. And then I say, now execute this code located in heap, not in the code section. So that is like, but now if my system says no, heap can only be written but not executed, then I will fail. Okay, done with this? Okay. ROP, this is an interesting thing. And okay, here is like a little change in the plans. Next paper, my plan was to cover ROP, return-oriented programming. The paper is interesting, although it is like a long paper, like 30 pages. 34. You want some sure? Have you started reading?
A little bit, yeah.
A little bit, yeah. Okay, so then I think the issue is like if we try to cover the ROP paper, we will not be able to completely cover this one. And even what we can do is like I can give you in the next week an example from the ROP paper, like so you guys have a gist of what these things are and how they work. But you don't need to read the whole paper. Let's allocate this week and next week to finish this paper. Okay. So, but I can give in next week an example of how ROP return-oriented programming works. Okay. Okay. So how ROP works? So actually, when they said that okay, you cannot execute your injected code because we are giving this protection, writable or executable, not both. So they said, attacker said, okay, if you don't allow us to inject the code, we can repurpose the existing code to achieve our malicious target, whatever we want to do, okay? And for that, what you like, the basic idea is this one. So let's say you have a huge body of code, like maybe thousands of lines, let's say. And like you have so many assembly instructions, right? When you translate, definitely you will translate in assembly and connect to binary. So you have like thousands of codes maybe of assembly language, lines of assembly language. Now the issue is like, what is the program itself? It is just an arrangement of the instructions, right? If I arrange those instructions in one way, the map program will do something, one particular task. But if I arrange those same instructions as a subset of those instructions in a different way, my program will be doing something else, right? So now let's say all of these are some instructions which are mapped into the address space of the victim. Like for example, a library, okay, like libc. Okay, so actually return-oriented programming is a more general form of, there is another kind of attack, libc return attack. Okay, so return-oriented programming is a more general form of libc. So now let's say you have this like so many code. Now what you can do is like, and this is mapped into the address of the victim because this libc library is very commonly used. Okay, almost all C programs need it. Okay, so now what I can do is like, I don't need to inject a code. I can reuse these instructions. So for example, I wanted my injected code, which the code which I wanted to inject it was, let's say it was supposed to have an add instruction and multiply instruction and exclusive OR instruction. So in this sequence, right? And maybe another shift instruction. So, but I am not able to inject it now and execute because of that. So what I can do is I can look into this code, which is already mapped into the address space of the victim and see, oh, okay, where is add? Let's say this is add. Okay. Okay. And then I locate where is multiply. Let's say here is multiply. This is add, and this is multiply. And let's say this is shift, and this is exclusive OR. So what I can do is, if I have a mechanism to stitch these instructions together, stitch mean like I have a mechanism such that I can say, okay, start first this at this point, and once done here, jump to multiply. And once done here, jump to exclusive OR. And once done here, jump to shift. Right? If I can do that, I don't need to inject the code. Right? And return-oriented programming is a mechanism which lets you do exactly the same. Okay, but it still assumes that you have buffer overflow availability. Because to stitch these things together, you need to override the do the buffer overflow. Okay. So hopefully what I want to do is like in next week, at least I want to be like show you an example like, okay, this is the program, and this is like our assembly. How can you write this program by stitching these different gadgets together? These are known as gadgets. So how you can stitch together different gadgets and make a meaningful attack, make a meaningful injected code. Okay. Okay. So this is also done. What else? ASLR left. Who want to explain? I don't know how ASLR works, so you explain.
Randomizes the addresses for the code.
But why?
It randomizes its address randomizer for security.
No, but what goes wrong if you don't randomize?
You could guess where the functions are or pick up the code.
Yes. So the thing is like, for example, remember I said that either you can have an injected code or you can redirect the function pointer to a function where the victim don't want it to be pointed to. For example, scare, right? Scare function. Now, if I know that where the scare function is mapped in what particular address in the address space of the victim, it is easy for me to extract that address. However, if every time the system randomizes the location at which that scare function is mapped, even if I figure out that where is that the address, maybe by the time I use that address, that scale root function is not located anymore there. Okay. And as a result, my attack will fail. At most, what will happen that maybe like victim will see a segmentation fault. But having segmentation fault, maybe, I mean, some can argue it is more worse, but it will avoid your change of execution flow. Yes.
If C and C++ are memory safe, why industry or programmers haven't fully adopted more
Sorry, say it again.
If C and C++ are memory safe, why the industry or programmers in general haven't adopted safer languages such as Rust for I don't know, critical systems or important systems?
Yeah, so this is partially answered in first slide. Like, yes, maybe for new systems, you can use some memory safe language. But you cannot, how to say, completely replace all the existing systems, and C and C++ are one of the oldest languages. So like there is billions of lines of code. It's not possible to get rid of all of it. Second, yes, people have devised some mitigation mechanisms, which you can deploy even if you are using C or C++. So you can use on those mechanisms to, even like if the programmer wrote a vulnerable code, you can still use those mitigation mechanisms to raise your security level for your program. And third, which is also mentioned in the first slide, is like more lower level you go, more lower you go, and in terms of like ease of programming, more fine control you have and more performance you can extract. So that is like the reason. For example, that the main issue is like the main reason why still people use C++ because it gives you the right control to manipulate the memory as a programmer. Like, for example, you can access the different memory locations. You can map them into the address space. You can unmap them. So that is quite easy. That's the reason. For example, now Linux is used in so many systems, right? In all type of systems like server grade, desktop grade, embedded systems, so on. Now, and that is written in C. How can you say that, okay, how can you do that? That, okay, we are not going to use Linux anymore. And whatever is deployed there, we are going to like remove it, right? It's not easy. Okay, so don't we have time anymore? Okay, have you submitted the class participation forms? Okay, let me simply go over my list of questions. Maybe some of them are already covered. What is memory safety? Where the situation where you ensure that the program written in a particular language doesn't allow for these vulnerabilities like buffer overflow, integer overflow, format string vulnerability, right? So the language itself doesn't allow it. C++ will never detect it. What is type safety? In C++, I think do you know the concept of casting, type casting from one type to the other? And it is like, there are two types. One is explicit casting and one is implicit, which is automatically casted from one type to the other, depending upon whether you are going from the smaller one or to the bigger one, right? So this kind of typecasting can also create problems. They have given an example in the paper. I don't have the time to explain it, but basically the thing is like if you allow the automatic typecasting, then it can, in some situation, it can lead to the memory corruption. So if you like go and read the section where they are talking about double free vulnerability and double free attack. Okay. So how it can, no, not double free attack. Use after free attack. Use after free. And what is integer overflow? You have two numbers. Let's say you have a number and I ask you as a user, give me some value. and the number is, let's say, integer. Now integer can store a range value of range of values, right? Now, if you give me a value which is too big to store in that integer, then it will wrap around. And if it will wrap around and then I'm using that integer to index into some memory location, I will be indexing out of bound. Right? What is overflow explained? How digital flow can be used to achieve overflow explained, right? Just like this side, okay? Just because by overflowing, you can go into the wrong place. What a timing point is explained, right? And what is the use of the free array? I will explain next. ASLR. Yeah, okay, before you leave,